All right. Let's get our project open here. All right, so baby dies. We get that rag doll that has the baby dying. Right now, we're after a period of time, we want the baby to respawn, maybe at its original respawn point. Now, another thing that we kind of notice here is that when the baby dies, actually, that was kind of interesting. That was like really zipped. That looked better, whatever. Actually, that was okay. The camera didn't follow the ragdoll, which is what we wanted to do. Maybe the previous time the baby fell through the crack or something, something like that between the two of them, because we really don't want it to follow the baby down to oblivion. So what I'm going to do here is I'm actually going to create. Did we already do the? Yeah, so this is our baby respawn that we created, right? And this is going to be a, so this is the ragdoll for the baby's death. This is the respawn, and we decided that we were going to have that respawn move to the starting position of the baby at the beginning and then go invisible. Okay, so let's start by doing that. And do we already know about the respawn? So here's the respawn point ragdoll that I already hooked that up. It's my player. Yes, I did. And right at the beginning, we turn the renderer off for the respawn point. And then we set the respawn points ragdoll equal to the baby position, whatever. Okay, now and is it the baby that is colliding with the thing, or is it the other way around? All right, so this is where we hit the enemy. If we hit the enemy and we're currently alive, we're actually repositioning it there, right? I'm not sure why we're doing that, because we moved at the very beginning. When we first start the game, we're moving the respawn ragdoll to the same position as the player started at to keep track of that place.
Down there is the dead baby.
Oh, that's dead baby, okay. So this replaces that. So then we're going to say component, whatever, blah, 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 add force. Okay, so then we said after 3 seconds, respawn the player, and we talked about the invoke function at the end of class last time. All right, so I'm going to go ahead and create a function in here, private void respawn. And what we'll do for this one is we're going to go ahead and move our player. Now, we currently have our player's renderer turned off. So we're going to go ahead and we're going to move the player back to the position of the ragdoll. So this dot transform dot position is equal to this dot respawn point ragdoll dot transform dot position. So that'll put our invisible actual player baby back where the respawn point was. Then we're going to go ahead and we're going to turn the renderer back on. for our baby. And then we're going to go ahead and invoke that function. And actually, we probably should go ahead and turn alive back on as well. This dot is alive is equal to true. So we'll say invoke. What's the name of the function we're invoking? We're invoking the respawn function. And we're going to do it after 3.0 seconds. So baby dies, we get into this else if. We replace the baby with the ragdoll, making the baby invisible. After 3 seconds, we call a respawn. Respawn says, move the baby's position to wherever the original respawn ragdoll's position was. Turn the baby back on visibly and set the baby as alive. Oh, and I missed my death. All right, so there's our restart. All right, questions about that? All right, so next, let's go ahead and we want to get an enemy walking back and forth here. We'll kind of throw some scores up at some point. But let's get an enemy moving on the screen. Let's just go zoom in on the player. So let's go down to our assets and let's pick up a decent enemy. So here's our characters. We got this little king dude, right? Which are the ones that may come. So that's walking. I don't think that's walking.
You have to put your respawn under the name.
We shouldn't have to because we never actually disconnected the player from the camera. Did we? Yeah, so I mean we just took the baby that we made invisible down here when he died and shoved him back up here. So we never actually made any disconnects to anything. Trying to decide which is the guy. I think it's these four are the walking for this dude. So I'll highlight those, drag them into the scene, which will give us our new animation. Let's just call this enemy walking. This is going to be in our animations folder. Okay. And we'll go ahead and name this guy enemy. We'll scale him up. Okay, now it did give us a new controller. We do want a new controller for that enemy. Although, well, we probably could actually use the same controller as we used for the baby one just because we're currently only supporting walking and stuff. But if we want the enemy to have some other animations potentially, probably have a second controller for our enemy's animations. So we'll call this guy enemy controller. And right now our enemy only knows how to walk, so we'll just leave it at walking. So when I hit play here, our enemy is sitting there walking. He's going a little quick, so we'll go ahead and just slow him down a bit. Maybe make that 0.25. Looks reasonable enough. Maybe 0.4. All right, we'll say that's good. All right, so now what we really want to do is we want to have our enemy kind of path back and forth. So when he's walking one way, he's facing us. Otherwise, he's going to flip around and come back the other direction. Right now, we'll have him moonwalk before we actually rotate him. So we'll just have him kind of go back and forth. So we need to start him on an initial direction. We'll probably say, let's go to our enemy here. Let's go ahead and add the rigid body to this dude. Oh, we also need to add a box collider. Well, what does he already have on him?
You have a rigid body too.
Oh, thank you. All right, I can just say that, whatever. And a box collider 2D. All right, so now he's on the ground. And then we want to go ahead and create a new script for our dude to get him walking. Okay, so let's go back to our scripts. And let's create a C# script. We'll call this guy, just call it the enemy script, because they'll probably do some other things other than just walking. We'll double click on this guy. And what we want to do is we want to add force to the rigid body in a certain direction. All right, so let's give ourselves access to the rigid body. So we're going to experiment here with adding force versus translation versus a new tool that we're going to look at today called lerping. Okay, so lerping is a linear progression over time from one point to another point. And what we're really going to end up using that for is, think about in Super Mario Brothers where we have the mushroom. You jump up and the mushroom kind of comes up. So we want this sprite to go from here to here over like a, I don't know, call it a 2-second period or something like that. So what lerp does is it gives us a kind of a smooth animation between those 2 points. But lerping has its own kind of drawbacks where there's a slowdown kind of at the end of it because of the way it works, and there's some workarounds for that. But for right now, let's do rigid body. And then in start, we'll say this dot RB is equal to this dot get. Why isn't it updating? Let me kill Visual Studio real quick, relaunch it. This dot get component, rigid body 2D. All right, so now we'll have access to our rigid body. And then on update, we're going to say this dot RB dot rigid body 2D dot add force. And the force we're going to add is a vector2 dot, well, here we'll say left, so we'll have them come at us, times some strength. So let's give it a 5.0 or something like that, just for the moment. And I'm going to position our enemy a little bit farther down the game world here. Move him a little closer to the ground. Not a strong enough force. That should have been a strong enough force. Oh, probably need to attach the script to our enemy. All right, so now the enemy has that script. 50 is probably going to be too powerful. Yep. Just bouldered at it right at the... All right, so let's go back to 5. All right, so there's our enemy coming at our player. Now, something we notice here is the enemy is speeding up as he's going, right? Because we are continually adding force on we're doing this in update, right? So every single time we update, we are adding some force against that player, and there's no pushback to that player. What would happen if I added force right at the very beginning? Just add a force of 5, not doing it inside of update. He had an initial force, but what stopped him? Friction on the ground. All right, so the ground is giving him a little bit of, we can think of it as pushback. So we really want to have force over a period of time, but we want that force to shrink to kind of maintain a speed. So what I'm going to do is we're going to move this guy back. And I'm going to add an additional component down here. Was it delta? Is it time.delta? So time.delta time. So this is the amount of time that has passed since the previous frame. Okay, so we're going to add a force. So this is going to be, some fraction of a second. So 0.0, so it should actually shrink our force that's on here. And we might need to up our value a little bit here, but let's see if this gives us any sort of movement. Yeah, we need to up it. Let's do it 20. That still might not be enough. But this should give us a continual force. I guess let's go up by a lot. So like I said, this is a small number. So whatever this number used to be, we're cutting it way back because of that time delta. All right, so there's him moving some. Still a little slow, but consistent speed or more consistent speed. You do have some stuff with the how much you have pushback from the skidding on the ground plus the frame rate on the machine, if it fluctuates at all. All right, so now he's moving there. Now, one thing that seems a little weird there, though, is that we have this kind of this timing where, like, okay, well, we're going to set this guy at speed 437 just because that's what felt right or something like that, where we might decide, you know what, I really want this guy to move from here to here over 8 seconds, some period of time. Okay, so let's look at the documentation, and we're going to bring up this Unity lerp. So it's actually part of the Vector3 class, but that's okay. All right, so we're going to have a transform. It's going to be the start and the end. So we're going to put a couple of little empty game objects in there to give ourselves kind of bumpers, if you will, for our start and end point. And we're going to have the speed at which we want to move. And we'll have our start time and the length of the journey, how long we want it to take. So notice here in start, we're going to set start time equal to time.time, which is a fixed amount of time. That's delta time is the change in time since last frame. Time.time is current time. All right, so we'll have the current time as our start time when the script first becomes active. Then we'll have the journey length being the distance between our two markers, start and end marker. All right, and we're going to put two empty game objects in there for our start and end. Then on update, so once per frame, we're going to figure out how far we have covered up to this point. So we're going to take the current time on this frame minus the start time times the speed. That's the distance we've currently traveled. Then we'll figure out what fraction of the journey we've completed. Distance covered divided by our journey length. Then we're going to go ahead and we're going to set our new position to be the result of a lerp. So this is a linear transformation, so it should maintain speed. And that lerp is going between our start marker position, our end marker position, and what fraction of the journey we've already seen. Okay? So let's give ourselves this setup, and we'll see that it's going to be pretty consistent. We're going to see a little slowdown right at the very end as he's coming into his kind of his landing, if you will, at his destination. But this should give us a more controlled way of giving us something that happens over time, rather than just randomly picking a force to put on the guy. Okay, so let's steal some of these things. All right, and then let's go ahead and give ourselves our start and end markers. I'm going to go to my assets. Here's like a little sign guy. We'll blow that up a little bit. We're going to use the little signs as start and end markers. We'll make them invisible once we start it up, but this is seems to be a reasonable place to so we'll call that guy end marker. We probably could actually make him the start marker. I think that's what we'll actually do. That'll give us more flexibility for just putting the guy wherever we want him as a starting point. So this is going to be our end marker. We'll click on our enemy. Here's his script. And we're going to go ahead and just fill in the end marker. Okay. And I'm going to come back into the script here. I'm going to make start marker private. And then in start, we'll say this dot start marker is equal to this dot transform. So we'll go ahead and just get the position of our enemy when the script first starts, and that's where we're starting from. All right, and then we can adjust the speed out there, but we have a default speed of 1.0f for right now. We'll mess with that. Okay, so let's go back over to the documentation here. So in start, we go ahead and we grab our start time and we calculate our journey length. So journey length is going to be the distance between these 2 points, our start marker and our end marker. Now we are using vector 3s here instead of vector 2s because they're the guys that have those functions. I'm not sure if vector 2 has a distance. Okay. Let me actually check something else here. Oh, we have our lerp on there too. That's fine. So we should be able to convert all these to just vector 2s then. I mean, really, the difference between a vector 2 and a vector 3 is that the z is constant. They're both just struct data structures. Okay, so that'll calculate the distance between those 2 points. And then inside of update, rather than adding force to our rigid body, so in this case, our enemy wouldn't actually need a rigid body. We'll leave it on there for now because we have to decide how we want our player to interact with that guy. But we'll calculate the distance we've covered up to this point, the fraction of the journey that we're currently on, and then we'll update our current dude's transform position to be the result of calling, we'll do this vector 2 dot lerp, from our start marker position to our end marker position, and then the fraction of the journey. Okay, and what lerp does is it linearly interpolates this over time. So it should move at a constant speed since it's happening over linear time. All right, let's just test this real quick and I'll pop the code back up there. I have a feeling that our speed is going to be a little bit slow right now. So let me click on the enemy. Let's set the speed to 10. Oh, it was not too slow. Even 1 was too fast. Let's do this at 0.1. All right, it's a little bit better. All right, so now he's arrived at his destination. Now, we really would like him to go back and forth between these two things, right? How would we handle that based on what we know so far? Once he hits this point, how do I make him go back to the other point? What do you think?
Switch the start and the end marker.
Okay. I suppose we could do that. We can decide that we want the other guy to be, let's start with one question. How do we know we've reached our destination? Let's start with that part of it. Because at this point right now, is my guy still trying to lerp to the destination? Yeah, he's still, that guy's an update. He's still working on it. He just doesn't have a whole lot of, he has nowhere to go, right? Every single frame, he's deciding how far am I from my destination. I'm 0. He might be coming up with some number slightly bigger than 0, but, close. He's really close to it. And he's trying to lerp there. Go ahead.
You could have some boolean that says if you're within this range, this is true, and you need to go down to this function instead of going that way.
Okay.
And then when it gets close to that one, just
so maybe we can have a move left and a move right, and that kind of, as you pointed out, flip flop our start and end points. So let's kind of modularize those a little bit. So let's go ahead and let's do a private void move left. And inside of this one, let's put, yeah, let's go ahead and put all this code. And then for right now, we'll just always call move left in here. And what he's saying is we're going to start conditionally calling move left. All right, so every single time we'll call move left, we'll figure out how far we've covered based on us continually moving left, what fraction of the journey we have left. What I'm going to do is I'm going to go ahead and I'm going to print out frac journey. Let's see what that number looks like. Because what we're really doing is we're trying to decide what would be a good number to operate off of for us having arrived at our destination. Okay. So we'll go ahead and run this. Let's look at our console. So here at the very end, we're 0.04, 0.05. Point 1. At the beginning, we had 0. So 0.1 is, we're basically there, correct? But for a while, we were at like a 0.09. So maybe we can say as long as our fraction of our journey is 0.09 or less, keep moving left. Otherwise, start going right. The other thing we could calculate is current distance to our destination. So what if I came in here and I said, let's just print out, we'll print in here instead. Instead of printing out fraction of journey, why don't we print out the distance between where we currently are and our destination. So let's do vector2 dot distance, this dot transform dot position, and end marker dot position. So now we're going to get, instead of a percent towards our goal, this is going to give us the actual physical distance we are to our goal in units. Okay, so when all is said and done, we're kind of at like a 0.4. So could we say that we are at our end goal when the distance is less than 0.5? Does that feel about right? Now, what would happen? So we might just call this guy move. And then we can ask a question on this vector 2 distance. If the distance between our current position and our end position, if that guy is less than 0.5, then go ahead and flip our transforms, our start and end markers. So if we're close to our endpoint, that was the numbers we were getting, right? Yeah, less than 0.5 was right up next to it. So if we're less than 0.5, then go ahead and change our begin and end markers and still call move, but now move will be calculating it based on a new begin and end. Now, we do need to consider, though, a new start time. Okay, so let's do it without the start time change. So if this is true, then what we want to do is we're going to go ahead and say transform temp is equal to this dot start marker. Then we'll say this dot start marker is equal to this dot end marker. Then this dot end marker is equal to temp. So we'll just swap those two. And then we'll always call our move function. We just potentially have swapped our begin and end point. Let's go ahead and run this. All right, so he slowed down. He definitely did something different there at the end, right? When he started noticing he wanted to turn around, we saw that he's kind of making the decision at least roughly the right time. What we need to do here is we need to update our start time. And then journey length actually should be the same. We're going to have the same distance to our other point, so we don't need to update the difference there. So let's update our start time inside of this. Oh, I think he's getting stuck on the end. Just move that over a little bit. What is happening to him? He's like falling into a little hole. Let's go back into the script. Here's our start marker. We really could, just for the sake of argument real quick, I want to turn the rigid body off on that enemy. That way gravity doesn't impact him. But you see, as he was going across there, he was sinking in. It's like quicksand. Didn't we have this at the end of class last time where our world was kind of like moving? Like when we went to one end versus the other, wasn't it teeter-tottering? Or was that not in here? That was in here. Because you see him sinking down. If you watch him, he doesn't even have a rigid body on him. But he's like inside the ground. You can turn the box collider off. How is that happening? He doesn't have anything associated with him. He has no gravity. I mean, if we put the rigid body back on him, we can then constrain his position on Y so he can't go up or down. Oh, he's still sinking. Why is that? All right, so if his position is constrained, that means he's not moving. It's the floor that's moving. And why would the floor be moving? Let's add rigid body 2D to the floor. And I'll just constrain his position on Y. Oh. Let's constrain it on X. I have the rigid body constrained on both sides. That should not be able to move on X or Y. All right, he's still sinking. What is causing him to sink? Is he sinking and everybody else is?
He's not moving on like,
Oh, he's not moving at all yet?
it's giving me an error that it can't assign the transform for some reason.
Maybe we just stumbled upon a true intelligent AI. Zombie Baby has actually created quicksand for his movement. Here, I'm just going to elevate him a little bit since we don't have gravity turned on for, well, since we're constraining him on Y. No, he's still falling.
Is it because the lyric works vertically too? So the sign's Y is lower.
Oh, that could be it.
It moves down slowly.
Yeah.
So it can move up if we move the sign up.
We're just dragging him into the ground.
I think so.
All right, well, so now he's there, but he's not going back. So once the distance is less than this, let's just make sure we're getting inside of here. Do I save it? All right, so it got there. All right. Oh, it's flip-flopping back and forth because he's within 0.5 and he's never actually escaping that 0.5 distance. So let's give ourselves a Boolean for direction. Because that doesn't necessarily help us because we're going to be in a Yeah, we might not be able to do this on distance. We might have to look at a collision with that endpoint and then have him go back after he's collided. Because distance, we're getting stuck. We're just flip-flopping back and forth. So let's create a couple of private Boolean move left is equal to true. That's a bool. And we might be able to do it on distance now. So if the distance is less than 0.5, no, because it'll still fail us on the other end. Unless the distance becomes negative 0.5 on the other end. I think we should do it on collision. Let's just make sure he goes back the other direction first. So if it's less than 0.5 and we're supposed to move left, then go ahead and flip-flop everything and set this dot move left equal to false, or we just invert it. And then we'll call this dot move. So we never have a situation where we'll flip-flop again because move left will never be true again in our current example. So he should go down and then go back forever, or you know. He's not getting stuck there this time. Maybe we do need to if it's negative now, maybe we do need to recalculate journey length. Maybe it's a negative number now since we flip-flopped those two. flip-flop, start marker and end marker. That's what those 3 lines do. Reset time, because we're like a new move. Reset journey length. And then set move left to false. Then go ahead and call move. This will figure out what's the distance covered, and it should be basically 0 because we're on start time and end time. Start time and time should be almost identical since we just calculated it right here. Then we'll determine that the fraction of the journey covered that journey length. Let's see what that value comes out as here. Maybe we, instead of operating off a negative, maybe we need to just flip the 2. Okay, so it only did it once. Looks like I'm printing a couple of things. The journey length is a float. It's 0.49. Let's get our original journey length. All right, so the original journey length was 24. The second one was 0.49. Okay, so clearly not the right values. Let's try this, and then let's try multiplying it by -1. Journey length has not gone down. Well, no, journey length did go down, but I'm not adjusting it anywhere. It doesn't change in here. It doesn't change in here. It looked like I had saved. I definitely saved this time. Why would journey length be different? This happens one time, and I set it. I printed the first time. That was the 24. On update, this is not getting called. So why has journey length changed? We use the value inside here, but we don't change the value. That's that print. That's that print. I mean, it's printing out like I am still setting it. Okay. That's weird. I mean, I just removed a commented out line. And it went back to, oh, that's frustrating. Okay. So let's then say this dot journey length is equal to this dot journey length times -1. And let's see if that, if the negative value on lerp has them going back the other direction. So we should get a -24 there on the back end. All right, well, there is our -24, but that does not have him going back. So we might need to have a move right. Let's have that as move left. I'm going to just copy this. This is going to be almost the same thing. Says the enemy already, I have a variable for move left. Call that move L. Call this move R. In this case, we'll move from the end marker to the start marker. And then in here, we will not flip-flop them. We will restart start time though. We will not change journey length. And we'll call this dot move. Well, actually, after this one, we should have that if stay on its own because we're only going to get into that once. Then we're going to ask if this dot move left. If we're supposed to move left, then call move L. Otherwise, call move R. All right, so on update, if we are close to our endpoint and we are currently moving left, restart the timer, set move left to false. Then we ask the question, if we're supposed to move left, then move left, otherwise move right. So this should call our two different move functions where we're actually lerping between the 2 points in reverse. So I assume that lerp then does the math for going back to the other point. Why is he stuck on that? Let's make sure we're calling move right. All right, he's trying to move to the right. Those are our here's. What this seems to me, I want to print something here. We have our start marker being our initial transform. So I'm going to print out start marker here. Now my understanding is that transforms are structs, therefore we're not getting a pointer, we're getting a hard value. I want to find out what that value is in here. Where's the start marker? It should be the same as it originally was. But if it's not, if it's now a whole different value, that means that it is a pointer and that start marker is actually moving with the enemy. So you might be trying to move to that start marker, but the start marker might already be there because the enemy is right where we have it. If that's the case, then we just need to put a second sign there. Let me just print off the X for it. There's position X. There's position X. So there was the 13.76. Ah, -9. It's a pointer. Interesting. So I'll copy this. Call this guy start marker. We'll move him down here. Should be able to lower them a little bit. And then we need to give our script a position for that start marker again. Make this guy public. We won't set it here because we want it to be a static position. And then for our enemy, we need to drag in that start marker. He's moving. Yeah, so that's the speed thing. The start marker was moving with him before because he was the one moving. So now we can go back in and we can set his speed to a reasonable number. Let's set it to 1. All right, a little bit slow. Let's set it to 3. Okay. So right now we have him bouncing back and forth between those two things. Now, one thing we could do is we can actually start the I think I've kind of seen this before. If we start him here in the center, kind of close to the endpoint, I'm trying to think. I've seen this in Mario, where when you first come onto the scene and you see the turtle moving, the turtle is actually started a little bit to the left of a certain thing, and he moves, and that's what gets him hitting and turning around. Does anybody else remember that type of thing? Instead of having him going on his first thing, it's a long straightaway, and then hitting and turning back around. Instead, he's like here, and he moves to the right a little bit, bumps into something, and that's what gets him started. You know what I'm saying? I'm thinking that's the trick that they've used for getting this turnaround thing. So if we actually start him here and get him moving to the right first, within a second or two, he'll actually hit this box collider. And when he hits that box collider, then he'll turn around. We won't actually have him flip yet, just he'll moonwalk, right? He'll move this way now. And when he hits this box collider, then he'll move back this way. Hits this box collider, he'll move back this way, so on and so forth. Does that make sense? But we'll start off having him move to the right, actually. So with that in mind, these two guys need to be we're not going to do this based on a distance anymore. So we'll have him moving to the right to begin with, because move left is currently false. And then what we want to have happen we need to flip-flop these because we're having a move to the right to begin with. Okay. So that'll be our initial distance. So we're going to have him move to the right. Why is he starting all the way over there? Well, whatever. Maybe I just need to restart Unity. So this will be his initial position here. We want him to start moving here, hit the box collider, which then will tell him he needs to move to the left. Hit the box collider, which then tells him he needs to move to the right. So for your homework, have your guy bouncing back and forth using lerping and using the box colliders on these two wooden sign dealies. Does that make sense? Okay, we can't do it on distance because distance is only going to let us bounce back once. All right, I will see everybody on Thursday. Don't forget student, faculty, staff Bible study today at noon. God and Grub. You get free lunch. Just go into the cafeteria, sign in, grab a tray, get your lunch, take it down to the terrace room.